Okay, hi everyone. Welcome to the Graphs and Matroids seminar. Today we have Carla Groenland from Utrecht University talking about labeling schemes and universal graphs. Go ahead, Carla.
Yeah, thanks for giving me the opportunity to talk today. So everything I'll be talking about is joint work with Mart Bonamy, Louis Esperet, Cheryl Capoy, and Alex Scott. And yeah, I'll talk about both labeling schemes and universal graphs. There's actually two different works that I'll be talking about. But yeah, there's a bit of a connection between these two objects. So I'll first talk a bit about adjacency labeling schemes and induced universal graphs, and then I'll talk about sort of a new notion that we've looked at called isometric universal graphs. So let's first have a look at what is actually a universal graph. So there's a notion of a universal graph and an induced universal graph. And in an induced universal graph for a graph class, we want to contain all graphs in the graph class as an induced subgraph. So here I've written down all graphs on 3 vertices. And now we want to create a graph that contains all of these graphs as an induced subgraph. So we need to contain a triangle, so let's put down a triangle. And we also need to contain a graph on 3 independent vertices, so let's just put them down here. So now we contain these. And now we already contain one of the remaining ones, an edge and a single vertex. And we don't contain the last one yet, but we can just add one more edge. And now this thing was still an independent set of size 3. So this is also from the construction, you can probably see that this is the smallest example. And now the question is, how small can we make these things? Well, first of all, do they always exist? Well, there's one sort of trivial thing we can do. We can always just take the disjoint union of all graphs on n vertices if you want to have something induced universal for n vertex graphs. So what does that give us? Well, the number of graphs on n vertices is about 2 to the n squared. So there are some precise asymptotics that are known for this. And then you still have to multiply by n, but that doesn't really affect the asymptotic. So it's about 2 to the n squared over 2 is approximately the number you get by taking the disjoint union. So how much better can we do than this? Well, there's one other way of creating them, and that's through a labeling scheme. And if we want to do that, then we're given a graph, and now we want to assign labels to the vertices so that just by looking at 2 labels, we can decide whether there's an edge between the corresponding vertices. So I'll give a formal definition of this later, but let's first look at what it is in the picture again. So one way I can tell whether there's an edge by assigning labels, I can just number all my vertices as I've done here, and then write down what the neighbors are. So here I've written down that this name is 0 and it's adjacent to 1 and 3. And if I then get this label and that label, then I read off the name 1 from vertex V. And then in the list of U, I just check whether 1 is in there. And that way, from these 2 labels, it tells me whether in the original graph there was an edge or not. So note that this labeling scheme is going to have to work for every graph in the graph class. So when it receives the labels, it doesn't know the underlying graph that these labels were coming from. And again, the goal is how short can we make these labels? So one technicality is that we actually want these labels to be 0-1 bit strings, but that doesn't really matter too much. We can just write down the names with log n bits, and then we can use a 0-1 encoding, for example, to write down the neighborhood. So here it's not adjacent to itself, but it's adjacent to vertex 1, etc. So can maybe someone tell me something that we could still do to make these labels shorter? Does anyone see something I can remove from them? Then if anyone dares to make a shot. You're muted, Rose, if you were trying to speak.
I'm just thinking to myself while.
Okay. I was seeing your. Oh yeah, so maybe it's also not that easy to immediately see this. Well, one thing is, yeah, I'm assuming that there's no self loop, so we could not record the adjacency to ourselves. But also we've recorded now the adjacency between 0 and 1 at both vertices. So there's something to gain here because we get both of the labels. So something that we can do is we can just write down the vertices on a circle and just write down your adjacencies to the next n/2 vertices on the circle. So here the adjacency between 0 and 1 I've encoded in 0. And for example, the adjacency to 0 I've recorded here for the last 2 vertices. So now whenever I get 2 labels, there's always one of the 2 that has recorded the adjacency. And instead of using n plus order log n bits, we now only use n/2 plus order log n bits. And it turns out that this n/2 is actually basically optimal, as we'll see later. Okay, so this is the sort of informal definition of an adjacency labeling scheme. And from these adjacency labeling schemes, we can, as alluded before, we can get an induced universal graph. So it's sort of important to remember that there's this connection, but yeah, you don't really have to understand why this is, but let me just give you a bit of the idea behind it. Well, if we have a labeling scheme with labels of size fn, so that's what for our 0, 1 bit strings, then we have 2 to the fn possible bit strings. And that we just put as our vertices of our induced universal graph. And when do we put an edge? Because that has described our vertex set. Well, we just put an edge whenever the adjacency labeling scheme tells us that there should be an edge. Whenever you input these two labels and it outputs, yes, there's an edge. And now you can check that this correspondence actually works out. Well, I haven't told you the actual definition yet for an adjacency labeling scheme, but I'll do so later. But let me just show you in a little example from our previous construction of Moon's labeling scheme. So the names of the vertices are 0, 1, and 2. Those are the possible names. And now either they can be adjacent to the vertex with the next label or not. So here we know that these edges have to be present. We know that these edges are not present because there's a 0. And again, these edges are present, the other edges are not present. And now you can check yourself that this is indeed an induced universal graph for the class of 3-vertex graphs again. Slightly larger, but it turns out asymptotically that this is sort of the right answer. Okay, so this is why I didn't start off with the definition. It's a bit of a mouthful. So this is the definition for an adjacency labeling scheme. In the end, we actually, the labeling scheme itself, we call it sort of the decoding function. So the decoding function A, it gets two labels, which are just 0, 1 bit strings. And if you give it 2 of these bit strings, then it just gives you a 0, 1 response, which is just, is there an edge or not? So that's also what I've written down here below. And we say that this has labels of size fn for the graph class G. If for any n-vertex graph in G, we can assign labels to the vertices, which are 0, 1 bit strings of length fn, so that this sort of decoding property holds. And there's one last technical assumption, which is that distinct vertices must receive distinct labels. So this last property, it immediately gives us a lower bound on the label size. Maybe I'll try again if someone is willing to try to give me the lower bound that it gives you for.
You're working with the, so you're asking about for encoding all graphs of a given vertex size, or just for a given?
So just say we have a labeling scheme for an n-vertex graph G. Say that the class just contains a single n-vertex graph G.
So log n for the number
log n,
of bits.
basically, yeah. So we need at least log n bits for encoding. So this function fn, sorry, yeah, I sort of wanted the lower bound on this function fn. So we know that that needs to be at least log n whenever there is a graph of n vertices, indeed. So that is somewhat a lower bound, but there's actually a second lower bound, which will be more important for the problems we look at. And that's just by counting the number of n-vertex graphs in our graph class. So whenever we have an adjacency labeling scheme that uses fn bits, we can actually recover the graph itself from its sequence of labels, the labeled graph. Because I look at these labels, I just name them 1 up to n, and now I just ask all the time, like, oh, is 1 supposed to be adjacent to 2, yes or no? And that gives me back the original graph. So that gives us this upper bound that the number of n-vertex graphs in my graph class is at most the number of labels to the power n, because we're looking at sequences of length n. So this is a bit of a, so if we put this upper bound in and we rewrite it, we get the following lower bound on fn in terms of the number of n-vertex graphs. And this sort of trivial lower bound and this Moon's construction now match up really nicely, because how many labeled graphs are there on n vertices? Well, there's n choose 2 possible edges, and we can choose any subset of edges for labeled graphs. So this is the number of graphs. And if you now put this into my function, then what I get is that I need at least n over 2 bits, which we saw before was possible with Moonscheme. So this is very nice. This sort of construction from the 1960s was actually already tight for the class of n-vertex graphs. And note that this also gives an almost tight induced universal graph. And since then, this plus order log n term has been removed as well after a line of work ending with a paper from Noga Alon. Okay, so what is the first part of this talk about? It's about when else can we match this counting lower bound. So it's not always possible. There are some examples for which it's not matched, but all of those are not hereditary. And hereditary means that it's closed undertaking induced subgraphs. Well, why is this something natural to ask for? If you have a labeling scheme for a graph, you can also apply it for its induced subgraphs. So it's kind of natural to just plug your induced subgraphs into the graph class as well, because it will just increase your lower bound and the scheme will still work. So it's kind of natural to start looking at these hereditary graph classes. And what we can show is that we can get a labeling scheme matching the lower bounds up to an additive term of little of n. So note that what's hidden a bit here is that this result is not interesting for hereditary graph classes for which there's not that many n-vertex graphs in the graph class. But for things like triangle-free graphs, perfect graphs, this all gives tight results, or like asymptotically tight results. And for example, for those two graph classes, we use n over 4 plus little of n bits with our results. So this little of n term for us is also quite bad because we use Semerades regularity lemma to prove it. So yeah, I guess not everyone is familiar with the results, so it's not going to be important for the rest of the talk. But I'll just quickly try to give you some idea of what the lemma says. But if you don't know this and you don't understand what's going on, that's also completely fine. So Semerades regularity lemma, you give it an epsilon, and then it gives you a constant. And then for any graph you give it, it gives you a nice partition. And one important property is that this nice partition is in a constant number of parts. So even if you give it 1,000,000 vertices, it will still give you the same, at most, a constant number of parts. And these parts have the property that the edges between the parts are somewhat well controlled. So there's some parts where you don't have control over these red edges, but there's not that many of them. So it turns out that we can shove those into our little of n term. And then this is quite a usual technique in this tool. We split them into edges of sort of high density and low density. And it turns out that we can handle those in a separate way as well in our little of n term, and that the thing that's really going to determine our leading term is these blue edges, which we have a lot of control over. So given these parts, we can sort of look at this reduced graph, and then there's a lot of Semerades regularity lemma is very well studied, and there's a lot of sort of connections known as well with hereditary graph classes, and we sort of can start applying that machinery to get their leading term from there. So I've repeated it a bit in text here. So one of the really important parts here, as I mentioned before, is that this number of parts is constant. So what does that mean for us? Well, anything that's constant, we can just add to our labels because that just becomes our little of n term. So in fact, we can make sure that every vertex knows this same sort of underlying picture that I've drawn here that's sort of available to every vertex in the label. And now there's a bit more technicalities involved here, but the red and the gray edges, it turns out that we can reduce that to encoding an epsilon n adjacencies per vertex. And I'll tell you a bit more on the next slide how we can put that into our little of n term. But sort of these bits, they go into our little of n term. And now for this red-blue graph, just to give you an example, if you know that the blue graph the original graph is triangle-free, then the blue graph is also triangle-free. And as you might know, triangle-free graphs, instead of having n squared over 2 edges, they have n squared over 4 edges. So that's why we get our n over 4 term there, because then we spread those out over our vertices. So that's sort of the broad idea of how this proof works. And I'll just tell you a little bit now about this step, because I think it's also uses something interesting which I hadn't seen before. So now what we want to do is we want to encode a small number of adjacencies for each vertex. So each vertex is just going to write down a list of its neighbors, as we saw before, basically. And one way we can do it is we can just write them down. So then we need to write down the names of the vertices. So that takes log n bits per vertex. So if you have a subset of size S, that takes us S times log n bits. So this is sort of fine if the size of S is not too big, but if we have the size of S equal to epsilon n, then this is not really good enough. And now you can start wondering, well, how many bits do we actually need? And information theoretically, if you want to determine this, you just look at your number of options and then you take the log. And that tells you the information theoretic minimum of how many bits you need to encode if you already know that the objects come from a certain universe to sort of give them a label. So in our case, these were the subsets of 1 up to n of size epsilon n. And if you take the log of this, then you can upper bound it by something called the binary entropy function of epsilon times n. And the only thing you need to know about this is that this term will tend to 0 as epsilon tends to 0. And that's why information theoretically we can put this into our little of n term just by doing counting. But yeah, there's one sort of technical detail that we have to deal with in our paper, and that's that we actually want something efficient. So we don't just want to have these labels that sort of have this sort of local preservation of adjacency while nicely spread out over the graph. But we also want the labeling scheme to be efficient, which means that we can construct the labels in poly n time. That's not really that much of an issue. You just need to get some algorithmic version of Semeradi's regularity lemma. And we need to decode the sort of thing that we didn't know immediately what to do with is the decoding by inspecting a constant number of words. So what we want is when you give this function the two labels, it can only look at a constant number of words, and then it needs to give you the answer. So I'm saying here words instead of bits, and this is a bit of a weird technical notion that's in this line of work. There's this model called the word RAM model, which allows you to just basically put something down in your alphabet. So k words are k log n bits because they're just elements from 1 up to n. So we can look at some constant number of elements from 1 up to n in our label, and that's everything we can do. And from that we need to find the adjacency. But it turns out that a lot of clever people have actually solved this problem for us as well already. And there's this construction called King dictionaries, which allow you to do this encoding for families of subsets of 1 up to n, which both achieve a label size near the information theoretic minimum, and also allow you to just inspect a constant number of words and answer whether a certain element is in our list. So this will be necessary for us because we want to decode these adjacencies. So we want to start checking, oh, in this list, is there the vertex that we want to know whether it's adjacent to it or not? Okay. So yeah, this is sort of the broad outlines of the techniques that we use in our to get the previous result. So the one of the things, so now I've presented it to you in a certain way, but this was of course not the way that we found this result. And in fact, we were originally working on reachability in digraphs. And it was sort of known that this is maybe equivalent to adjacency, in some sense equivalent to adjacency labeling in comparability graphs. And then we generalized it to all hereditary graph classes. So the result that we wanted to improve was from a paper of Juleba-Krakowski and Jan Kresky, who got a bound of n over 3 plus ditto O of n, and we wanted to improve this to the asymptotically best bound of n over 4 plus ditto O of n for reachability in digraphs. So that means that we have a directed graph, and we have two vertices in there, and we want to know if there's a directed path from one to the other. And now from our main result, because comparability graphs form a hereditary graph class, we can immediately get this result for those as well, an asymptotically optimal result. And also for comparability in posets. So that's just, we have a partially ordered set, and we want to know whether two elements are comparable or not. And for this setting from this slide, we also have a second proof, which doesn't use Semeradi regularity lemma, but this is completely elementary. And that makes this little O of n term a lot better. So that allows you to make it sort of a really true smaller order term. and also if the scheme is efficient. Because I didn't really say it here before, but to get this one efficient, we can actually not really do little of n, we can do delta n for every delta greater than 0 from the Semerady proof. But here we can also get the efficient scheme with a true little of n term. Okay, so these are some corollaries of it. And from the beginning of the talk, we introduced this induced universal graphs. Of course, we get this as well. We get for hereditary graph class, we get sort of asymptotically optimal induced universal graphs. And one of the interesting open questions here, I think, is what kind of structure can we impose on this universal graph that we obtain from the labeling schemes? Because actually, it can look in all kinds of ways. And in particular, we are not guaranteed that the induced universal graph that we get actually belongs to the graph class. And in general, you might not really care about this, but if you want to get, say, a universal poset, so a poset that contains all posets as induced posets, then our scheme doesn't give you this because we don't know that our labeling scheme for comparability graphs actually gives you a comparability graph. And in fact, you might expect that our labeling scheme, I think it just doesn't. So yeah, you can get a universal poset of size 2 to the n squared over 4 just by taking disjoint union. But if you want to do better than that, then you from just counting, you should be able to, or you should expect that maybe you can get one of this size. So this is one of the open questions that we leave behind. Are there any questions so far about things that I've talked about? This is also the moment that I would let my cat appear, because I'll switch a bit slightly in topic now. It's also a good moment to wake up again. Because for the remainder of the talk, I'd like to tell you about some other results that are a bit more in the direction of this question of what kind of other properties can we put on these universal graphs. So now, instead of wanting induced subgraphs, we're going to look at isometric subgraphs. So this is sort of a strengthening of the notion. So for an induced subgraph, so isometric subgraphs are in particular induced subgraphs, but now we also want the metrics to coincide. So I've written that down here, but what does that really mean? Well, if we look at the 3 vertex graphs here below, then in the left-hand side, it's not an isometric subgraph, because this vertex all the way to the left, we can shortcut to the vertex to the right. So in the whole graph, these 2 vertices have distance 2, but then if we just look in the subgraph, they have distance 3. But here on the right-hand side, it is an isometric subgraph because there's no sort of shortcuts by the rest of the graph. And now what we want to get is a different notion of universal graph, namely an isometric universal graph. And we want to contain all graphs, not just as induced subgraph, but really as isometric subgraph. So this really makes it a little bit different. So we can still take the disjoint union of all n vertex graphs, that still works fine. And that gives us something like 2 to the n squared. But can we now, so for the induced universal graph, the right answer was 2 to the n over 2. Can we still get this linear term here in the exponent? Was something that Peter Winkler asked. So the other 2 things that constructions that we looked at, we had this disjoint union first, and then we had this labeling scheme. So the JCC labeling scheme won't necessarily give you this isometric universal graph, otherwise this would have been a boring talk. But also another type of construction that people have considered, namely random graphs, also doesn't really work. So random graphs are sort of decent for induced universal graphs. They're not optimal, but they do okay. But for isometric, they're going to be very bad because they have diameter 2. So they can only contain graphs of diameter 2 as isometric subgraphs. So that doesn't really help us directly that much. So a sort of natural direction is to try to find a different notion of labeling scheme, because that was really useful for the induced universal graphs. But what should this notion be? there's the notion of a so-called distance labeling scheme that people have investigated. So from the labels, instead of knowing whether the vertices are adjacent, we're going to decode what their distance is. And it turns out that this doesn't work. So you can get the distance labeling scheme from an isometric universal graph, but not the other way around. And we introduce a new notion of a labeling scheme, which does give us isometric universal graphs. And here, instead of giving it two labels, we're going to give it a single label. And instead of decoding just a single distance, we're going to ask you to give us all the distances. So you give it the label of a vertex u, and now it's going to return to you the distance to all the other vertices in the graph for a fixed order on the vertices. So this will always have sort of the same order. And as I said before, we're going to have this sort of implication. So the distance vector labeling, it's enough to get our isometric universal graph. And this isometric universal graph, it does give us a distance labeling scheme. But this other direction doesn't work from this existing notion to this one. Okay, so just some small observations about this distance vector labeling scheme. So we'll always have some zero somewhere here, and that will tell us where in the sequence we are ourselves, because there's only one vertex at distance 0. And also we can retrieve the adjacencies from the labels, because if you give it two labels, you can read off its own sort of name from the unique index with a 0, and then you just, in the other sequence, you just look at the distance, and if it's 1, then it's adjacent. If it's not 1, it's not adjacent. So those are nice things. And there's one sort of trivial thing you can do, which is also always very nice. Namely, we can just put down the distances as our labels, and now we don't have to do any decoding. So that's an example of a distance vector labeling scheme, which is, we just haven't done any compression. So we're quite wasteful, but it does work for the definition. So let's try this sort of most silly option. So I've written it down here, and now let's try to construct an isometric universal graph from that. So what are we going to do? We're going to put down the labels as the vertices, and then we're going to come up with some condition of when we put the edges. So here, for example, the vertex 0, it has distance 0 to itself, 1 to vertex 1, 2 to 2, 3 to 3. Vertex 1 has distance 1 to 0, 0 to itself, 1 to 2, 2 to 3, etc. And now we want to make sure that there's no shortcut somewhere else in the graph. So what we're going to say is that we're going to put two labels to be adjacent. Exactly, well, there has to be some difference somewhere because we don't want self loops. But now we're also going to ask you to have all the coordinates differ by at most 1. So that's what this infinity distance tells us. All the coordinates differ by at most 1, and they're not the same. So now if we look in our graph, can we get a shortcut? Well, let's focus on the first coordinate. So in 0, we have distance 0 to 0. And where can we go? Well, we can only change this 0 by one thing. So we can leave it 0 or we can make it 1. So we can move somewhere here in the graph. And then in the next step, we can sort of step back to the previous one or stay on the 1 coordinate, or we can go to the 2. And then we finally need to end up on this side of the graph where there's a 3 for the distance. So in the end, we can sort of track this coordinate. And this way we can prove that it's indeed an isometric subgraph, namely all paths from 0 to 3 have length at least 3. Okay, so now what have we done? Well, when we look at our label size, it was these are n elements to the power n. So we contained an isometric universal graph on 2 to the n log n. That wasn't exactly what we wanted to get. We wanted to get something linear in n. But we can do that as well with some further tricks. So our main result says that there is an isometric universal graph on 3 to the n plus order log squared n vertices. So this is probably not optimal. You can probably do better than that, but this is our best result. So I'll just tell you a bit now about these tricks from distance labeling. So these were tricks to get this other labeling scheme I told you about to get better schemes for those. And then we sort of adjusted them to the other setting. Well, some of them we reinvented and then found in the community, in the literature, of course, how these things always go. So this was a really nice one, I think. So instead of storing the distances like this, which we want to get, so the distance from U to all the other vertices, we can also store some other linear combination of them. We don't have to store them like this. And that we can use to sort of bound the number of options. So what I'm going to do is say I have a Hamiltonian path in my graph. Then I'm going to label my vertices 1 up to 7 following this Hamiltonian path. And why is this good? Well, if I now record the distance from U to V2 minus the distance from U to V1, well, say this is my vertex U, then my distance to V1 is going to be at most my distance to V2 plus 1. And my distance to V2 is also going to be at most my distance to V1 plus 1. So this difference is going to lie in -1, 0, or 1. So this list over here, it takes a lot less to store because we still have n options here, which I haven't really written down, but you'll forgive me for that. And then we have, for the rest of them, we have 3 to the n options, which is this 3 to the n that we were aiming for, basically. And now we can still get our list of vectors from here. Namely, for example, if we want the third option, we just sum the first 3 elements, and then we get this one. So it's quite easy to see that these sort of systems of equations, they have the same information. Okay, so this works if our graph has a Hamiltonian path. That's already very nice. So what do we do if it does not? And there's a second, which I think is kind of, if you know about separators, this is a really obvious thing to look at. A separator in a graph, it's a subset that you can remove so that the parts that fall apart, they don't have edges between them. So now we know that any sort of path from A to B, it must go through the separator. So if we want to know the distance from A to B, we just need to know the distance from A to the separator and the distance from B to the separator, and then we can add that up. So there's sort of a generalization of this called hub labeling that's used quite a bit in the distance labeling community, where not like the separators might sort of be personal to the vertices. But this, for example, in planar graphs and things like this, we also get much better results using these kinds of ideas that we just have to, if we have a separator, we just have to record the distance to the separators. And for general graphs, what we end up doing is we take a depth first tree. So what's good about depth first trees? Well, each vertex can only be adjacent to something on the path from itself to its root. So for example, if I take a vertex here and a vertex here, then whenever they have a path to each other, it must go via something on this path. And there can't be sort of direct edges from this one to that one. It needs to sort of go through a common ancestor. So actually, yeah, this gives us sort of a good hub labeling in some sense. And what we do in our scheme is we write down the names of our ancestors, we write down the distance to our ancestors, again, using this, converting it later to this ±1 trick. Because for our ancestors, of course, we know that they nicely lie on a path. And now we just need to check that, yeah, there's some sort of technicalities to check now that this is sort of enough information, that if you know the distance from this one to, and from the other one to their common ancestors, that's enough to do. And there's one other trick here that I won't really mention, and that's sort of to compress these names, because we also, it turns out we can't just blindly write those down as well, but there's some further tricks hidden there. But the main idea here is that we can sort of get sort of personalized separators which nicely lie on a path, so that we can still use this sort of ±1 trick. Okay, so let me finish this talk with some questions which I think are still interesting. So I'd mentioned before this question of this universal poset, which I think is nice. But for the question that we started out from when we can match the counting lower bounds, we actually only handled graph classes which were dense, and we didn't handle graph classes of this form, because then our little of n term is just the leading term. And there's actually an old conjecture about this from Cannon, Nauer, and Rüdig, which says that if we have in a very different regime where we actually have very small graph classes, that then this counting lower bound is tight. So remember from the very start of my talk that this log n, that's also a lower bound just to give them distinct names. But it's also from, if you plug in the counting lower bound, then this is also, log n is also what you get. So for some hereditary graph classes of this form, this is known. For example, for planar graphs, you need log n is the right answer. But this is not known for this conjecture is still open and could also very well be false. And from the second half of the talk, of course, yeah, our construction, it's the sort of lower bound you get is the same as you get from counting. So that would be order 2 to the n over 2, and we can get 3 to the n. So there's still a bit of a gap here, which I think would be interesting to close. And another thing that I find sort of interesting about their work is this new notion of a labeling scheme that we've introduced, these distance vector labeling schemes. So I think it's quite interesting to see, is this actually different? Like, do you need more information here than for the much weaker notion of just a distance labeling scheme? And for those, it's also not known yet what the right answer is. So the best scheme for that, I think, takes what we do, but then divided by 2, because they can sort of do Moon's trick again. But yeah, it's still very much open what the best bounds are for those. And it's not clear whether these bounds will be the same as for the isometric universal graphs if we take sort of the log. Okay, well, thank you very much for your attention.
Thank you so much, Carla. So let's do a round of applause. If everyone could unmute yourself, and then I'll count to 3, and then we'll clap. So 1, 2, 3, clap. Pretty good. Okay, does anyone have any questions? You can just go ahead and ask.
Yeah, okay, I've got a question, which is, so I haven't looked up to see if any of the more recent papers talk about this, but I'm wondering if you thought about this question for classes of bounded twin width, for instance, because there's all these papers saying that the classes are small, and so I guess they're a particular case where you want to verify the implicit graph conjecture.
Yeah, I haven't looked at that. I'm not completely sure as well. Besides planar graphs, what they can do. I think that the paper on planar graphs probably does sort of, yeah, a bunch of sparse graph classes.
Gotcha.
But I'm not completely sure what they do. But yeah, I think that at least I'd heard that there's also people that believe that this conjecture is just false. I think it would also be interesting to. I think a counterexample would also be interesting, and also actually. Matching this counting lower bounds, I forgot to say that, but it's actually kind of a tough question as well for a different reason, which is that I think already sort of the counting lower bound itself is not very well understood. So the number of n-vertex graphs in sort of arbitrary hereditary graph classes, for the dense case, it's much easier to have this sort of notion of a coloring number that determines it. Whereas for the sparse ones, I think it can sort of fluctuate in behavior quite a bit as well. But you can, of course, still ask whether it keeps sort of following this function nicely. That would sort of be the question that I would be interested in. But yeah, it's probably maybe easier to find a counterexample than to prove it, is my feeling for it. But it doesn't mean that I don't believe it's true. It just, yeah.
Right. Thanks.
Does anyone have any other questions? Actually, could I just have a look at the moon's construction again?
Sure.
Okay. And why did it end up giving us one more vertex than the like the very first example?
Yeah, so in this very first example, I just sort of constructed it by hand, right? So this apparently, yeah, if you, so the correct lower bound is sort of n minus 1 over 2. So I guess for n is 3, does that actually work? Not really, right? But yeah, so at least one of the reasons why Moon's thing is not tight is that I've written down sort of the names at the start, which gives us this extra term of little, like big O of log n. So I think also probably, yeah, actually Noka Allen's result probably is only tight for n sufficiently large, I guess. I think he does have some sort of smaller error term somewhere still, but you can actually get rid of this order log of n term asymptotically as well. So for large enough n, you can, yeah, so first people did, I think, n over 2 plus 4, and then Noka Allen in the end showed that, yeah, this n minus 1 over 2 is actually just sort of the answer. But yeah, so this, you can do better than this, but it's, yeah, asymptotically, this log n doesn't really matter that much. But for small examples, I guess it's quite a big part of my label still, as you can see.
Right. I see. Thanks. Yeah, that makes sense. All right, does anyone have any other questions? I'll stop the recording there and we can have some informal discussion.